We're now going to discuss the advent of cyclic molecules, that is, chained molecules that come around and form a cyclic structure by connecting the two end atoms. These have a very important role in general chemistry, but especially in biological chemistry. We find there are a lot of cyclic molecules involved in biological chemistry. So our learning goals are going to be to understand the structure and property of small and medium-sized cyclic molecules. We're also going to look at the role of ring strain and steric strain as it influences the shape of these molecules. So let's get to cyclic hydrocarbons. This is another way to introduce unsaturation into a molecule, and we saw that in the last, when we did beta-carotene, we saw that its degrees of unsaturation were increased by the fact that it had two cyclic rings. Cycloalkenes are basically hydrocarbons with ring structures but no double bonds. So this is coming from the cycloalkane, the A ending there. So we might think of this as taking a chain of carbons that are hooked together and then closing that chain by attaching the end carbon with the first carbon. So you'll notice that the formula along here, each carbon has two other things it's attached to. If it's a hydrocarbon, that means there would be two hydrogens for every carbon, so its formula would be CnH2n, which is less than CnH2n plus 2. So for small ring structures, we're going to look at the smallest possible one is cyclopropane. We can't have a two-carbon ring structure because you need three to make a ring. So cyclopropane is C3H6. The carbons in this are obviously coplanar because it takes 3 points to define a plane. It has a very rigid structure. There's a lot of steric strain. If we look down one of the carbon-carbon bonds, we can see that the atoms are all perfectly eclipsed with one another. So there's going to be a lot of angle deformation of these, bond angle deformation of these, due to that eclipsed nature of the hydrogen atoms. Cyclobutane is also very strained, but it is slightly non-planar. By doing this, it achieves some smaller internal bond angles that relieve some of that strain. So here's what it might look like from the end. And if we look down one of the carbon-carbon bonds, we can now see that those carbon-hydrogen bonds have become more staggered. This relieves some of that steric interaction between them. When we go to bigger rings like cyclopentane, this is no longer an issue. Cyclopentane is very stable. Regular pentagon has angles of 108 degrees, so this is very close to a VSEPR model tetrahedral value. However, we still need to think about the steric strain between hydrogen atoms that are on adjacent carbons. These cause the rings to pucker, so it is non-planar. Most of the hydrogen atoms are staggered now as a result of this puckering. So here's a picture of cyclopentane, and then I've taken a look at each of the carbon-carbon bonds and looked at the hydrogen atoms down those bonds, and you can see that in the top pair they're pretty eclipsed, but they become more staggered as we move over to the left and the lower left. So this has got a variety of both staggered and eclipsed torsional conformations. It's about the best that you can do with this five-membered ring, but you can see that the steric interactions between those adjacent carbon-hydrogen bonds really are affecting the geometry of these cyclic molecules. When we get into cyclohexane, this no longer becomes a problem at all. The most stable conformation of cyclohexane is something called the chair conformation, and it looks something like this. Now I've drawn a red line to help you see where the carbon atoms lie relative to one another, and when you look at that edge on, it sort of has the shape of a lounge chair if you have a good imagination. So this chair conformation describes the geometry of cyclohexane, and when we look down the molecule, we find that in fact we're looking down two of the carbon-carbon bonds. We can see that all of the carbon-hydrogen bonds are perfectly staggered in that end view. All right, so by staggering them, this thing has virtually no steric strain at all anymore. This has reduced the steric strain as much as it possibly can while maintaining the tetrahedral geometry at each of the carbons and a relative cyclic structure when you connect all six carbons together. The internal carbon-carbon-carbon bond angles are 111.6, and you may remember in an earlier video we talked about linear butane, and we saw that the bond angles there were also 111.6. So this is just sort of the natural steric interaction between hydrogens on neighboring carbons in a linear alkane chain. So we can't do any better than this. This is as good as it gets when it comes to these cyclic compounds. We can also have cycloalkenes, which would be cyclic molecules that have a double bond. I should note that the cyclic structures constrain torsional flexibility. If you have a bunch of atoms that are hooked together in a ring, it's very difficult for you to twist about a double bond, twist about any bond in the molecule, simply because the ring structure inhibits that. When these cyclic structures also contain double bonds, this increases the rigidity of the ring. It's very difficult to engage in any sort of torsion about a double bond because to do so would break that pi bond. So these become very rigid planar type structures. And now you can imagine when you incorporate them in a ring, it's very difficult to have any flexibility there. So let's illustrate this with cyclopentene. Here is cyclopentene. It has one double bond and 3 carbons that are not involved in the double bond. And this is not a planar molecule because the carbon that is opposite the double bond is bent slightly out of the plane, but the other 2 carbons have to be in the same plane as the 2 that are involved in the carbon-carbon double bond and their hydrogens, because that's the nature of the planar structure of pi bonds. All right, but the 2 hydrogens that are attached to each of those adjacent carbons, as well as the 2 attached to the one at the end, all are in an eclipse conformation, so the one at the end bends slightly out of the plane in order to relieve some of that. Now when we look at cyclopentadiene, so we can also have cyclic molecules with 2 double bonds, we get a little bit different issue. All right, here we have 2 double bonds and only 1 carbon has as many as 2 hydrogens attached to it. The carbon with the 2 hydrogens is completely staggered relative to its adjacent carbons, and the 2 carbons that are attached by double bonds, they do have hydrogens that are eclipsed with one another, but there's no steric strain because they're bent further apart from one another. So this relieves the strain that would or otherwise occur between 2 eclipsed atoms. Now, it's also important to realize that whenever we have a cyclic molecule with a double bond, because it's hard to twist about a double bond, these are even more rigid structures than our normal cyclic molecules. So we're going to expect to see the rigidity of a molecule increase as first we become cyclic, and second as we begin to incorporate double bonds in that cyclic structure.